In this hour, we will be talking about superposition in circuits that has reached sinusoidal steady state. Okay. Let's begin by the following example. Okay, we have the following circuit. With three sources, namely three inputs, plus minus 2 ohm, 4 ohms, 5 Henry, 3 farads, an LTI circuit, and the inputs are given as follows: 2 cosine 2t plus 15 degrees, 4 cosine 3t minus 10 degrees, amps. This is volts, and here we have 3 sine 2t volts. Okay, 3 inputs, and the circuit is LTI. What we're asked for is find the current IT, which is the current flowing through the inductor in the steady state. Okay, so the circuit is LTI. The sources or the inputs are sinusoidal. Therefore, it seems reasonable to obtain or to solve the problem using phasor domain analysis that we have been talking for a while. Okay, so what we do is, therefore, we take the circuit, obtain the phasor domain circuit, and then do what we usually do with phasor domain circuits. But if you attempt to do that, you will immediately run into the following problem. Here we have an inductor of 5 Henry, and then in phasor domain circuit, it will be represented by an impedance that equals j omega L. Now the question is, what is the impedance of this inductor, okay, for this case? Because here we have a frequency at 2 radians per second, okay? So that would imply that the impedance of this guy will be J10 ohms. However, here we have another source at a different frequency, 3 radians per second, which would imply the impedance should be J15 ohms, okay? So what is it going to be? J10 ohms or J15 ohms, okay? So that's the problem when you have more than one frequencies, okay, throughout your circuit. In this case, we have 2 different frequencies. We have 2 sources operating at 2 radians per second and 1 source operating at 3 radians per second. So when you have more than one frequencies in your circuit, you cannot obtain the phasor domain circuit, or a single phasor domain circuit. Okay, so the problem therefore can be solved by applying or by considering one frequency at a time, and that we can do thanks to the fact that this is an LTI circuit, and we can apply superposition in LTI circuits. In other words, we can apply superposition in time domain and claim that I of t equals the sum of these 2 components, I1 of t and I2 of t. What's I1 of t? I1 of t is the part of the current I that's due to the sources operating at frequency 2 radians per second, and I2 of t is the part of I of t that corresponds to the input of oscillating at 3 radians per second. Okay, so more visually, therefore, what we're talking about is the following: kill the source operating at 3 radians per second, and what remains is the following circuit. Okay. This is a current source, therefore it being killed implies that we replace it with an open circuit. And then we have plus minus, so this is 2 cosine 2t plus 15 degrees volts. And here we have 3 sine 2t volts, okay. And we have 2 ohm, 5 Henry, 3 farad. Okay, so what we did is we killed the source and then considered the circuit under only these 2 sources active. Okay, and we called that component of current that's flowing over the 5 Henry inductor as I1. Okay. And then we can now kill the sources that oscillate at 2 radians per second and let this guy be active only. If you do that, then this is what you obtain. Cosine 3t minus 10 degrees amps. This is 4 ohm, 2 ohm, 5 Henry, 3 farads. Okay, so what we did, we killed these 2 voltage sources, that is, we replaced them by short circuits, and then the only active input in this circuit is this current source that's oscillating at 3 radians per second, and then that will generate some component of I, and that component we're calling I2. Okay, so since the circuit is LTI, we can apply superposition, and then we obtain 2 separate circuits. This circuit is oscillating at 2 radians per second, this circuit oscillating at 3 radians per second, okay? And then from this circuit we can compute I1 using phasor domain analysis techniques. From this circuit we can obtain I2, again using phasor domain analysis techniques, and then due to linearity we can apply superposition and add those 2 values, I1 of t and I2 of t, to obtain the steady state current, okay, passing through the inductor. Now, since this circuit now have just a single frequency, despite the fact that it has more than one input, we can represent this by a single phasor domain circuit. So let's do that. Okay. We have then the following circuit. Plus minus 4 ohm, 2 ohms. Okay. And now how about the impedances of the inductor and the capacitor? Note that we don't run into the problem that we ran into at the beginning, which was whether the impedance of this guy will be J10 or J15. Now we have just a single frequency 2, therefore the impedance of the inductor will be J omega L omega 2, therefore we have J10 ohms. Likewise for the capacitor, the impedance is 1 over J omega C. That produces minus J 1 over 6 ohms. Okay. The sources are 2, 15 degrees, and this is Okay, sine 2t can be written as cosine 2t minus pi over 2. Therefore, the magnitude is 3 and the phase is minus pi over 2. And that can be written in rectangular coordinates minus j 3 volts. Okay, so what we did is we transformed this circuit to, or from the circuit we obtained the phasor domain circuit. Okay, and then what we're interested in is this current I1. Okay, now using this circuit we can figure out I1. Once we have I1, that means that complex number, we have the magnitude and the phase, and then using the information that the frequency is 2 radians per second, we can easily obtain I1 of t. And we can do the same thing to I2 of t for 3 radians per second frequency, and we can combine those two signals to obtain I of t. Now, let's consider this phasor domain circuit, which has 2 inputs. Okay. Now, since it has 2 inputs, and since we've been saying that this is just like an LTI resistive circuit, okay, clearly we can apply superposition and consider only one input at a time for this phasor domain circuit. Okay, in other words, we can apply superposition once again. This time, okay, at first it was in time domain, and now this time we can apply it in phasor domain. Okay, so superposition can be applied in phasor domain also, and that implies that we can figure out I1 by simply considering one source at a time. Okay, where I1 prime is the part of the current due to one of the source, and I1 double prime is the part of the input due to the part of the current due to the other input. Okay, so in other words, we can kill this source, okay, and consider only this input here. Okay, minus J 3 volts, 4 ohm, 2 ohms, J 10 ohms, and minus J 1 over 6 ohms. And this current we're calling I1 prime. Okay, with a single input, it's a little bit easier circuit to deal with, and then by solving this circuit, we can easily figure out I1 prime. And we can do the same thing to the other source. Okay. And 4 ohm, 2 ohms, J 10 ohms minus J 1 over 6 ohms. And this is plus minus 15 degrees volts. Okay. In the second case, this source is killed and only active source is this one. Okay, and then this source will produce the I1 double prime component of I1. Okay, and then since the circuit is LTI, phasor domain circuit is also LTI, which means we can apply superposition. Compute I1 prime from this circuit, compute I1 double prime for this circuit, and then we can superpose them to obtain I1 prime of the original phasor domain circuit. Okay, now let me give you the answers. I1 prime turns out to equal more or less 0.25 plus J 13 amps in rectangular coordinates, and I1 double prime approximately equals 0.11 minus J 0.15 amps, and the sum will give us I1, which in polar coordinates approximately equals, okay, 0.37 with phase minus 4 degrees amps, okay. And since I1 is that, we can easily write down I1 of t, because the frequency for that circuit is 2 radians per second. Okay, for the sake of completeness, let's also transform this circuit to the phasor domain. This time the frequency of operation is 3 radians. Figure out capital I2. From capital I2 we can easily obtain lowercase I2, and then in the end we can superpose I1 and I2. Find I2t, what we do is we transform the circuit which we obtain by killing all the sources oscillating at 2 radians per second to phasor domain. Okay, in that case we have the following. Okay, 4 ohms, 2 ohms, and now the frequency of operation is 3 radians per second. So that means we're going to have different impedances for the inductor and the capacitor. Okay, we should have different impedances than J10 and minus J1/6. In fact, what we have is J omega L, which is J15 ohms, and 1/J omega C, which makes 1 minus J1/9 ohms for this capacitor. Here we have short circuit, and here we have short circuit because the sources at 2 radians per second are killed. And the only input in the circuit is this current source, minus 10 degrees amps. Okay, and now what we're after is, we're after this current, which we denoted by I2. Now, I2 can be approximately computed as 1.04 with phase 95 degrees amps. Okay, so here the frequency was omega was 3 radians per second, and here the frequency was omega 2 radians per second. And now with this piece of information plus the phasors that we have obtained, we can now figure out I1 of t for that frequency, I2 of t for that frequency, and then combine those two time domain signals, okay, to obtain I of t, which is the current that we measure through the inductor when all the sources are active. Okay, therefore I of t equals, or approximately equals, I1 of t. What's I1 of t? We look at the phasor of it. So I1 of t will have the amplitude 0.37. It's oscillating at frequency 2 radians per second, 2t, and the phase is approximately minus 4 degrees. Minus 4 degrees, okay? So that's our I1 of t. Plus we have the I2 of t. For that we look at the phasor of I2. The magnitude is about 1, and the frequency is 3 radians per second, and the phase is approximately 95 degrees. Okay, therefore this is I of t, which we obtained by applying superposition both in time domain and also in phasor domain. Okay, now let's move on to our next example. Okay, this time we have also a DC source along with a sinusoidal one. Amps, and here we have 18 cosine 2t volts. The parameter values are given as 3 ohm, 1 Henry, 1 ohm, 1/2 Henry, and 1/4 farad. And what we're asked for is the current passing through the 1 ohm resistor here. It's noted by I. Okay. So find the current IT in the steady state. So what is meant by steady state is the following. We have a sinusoidal source and we have a DC source. Again, we can consider, thanks to superposition, one source at a time. Now this guy will produce in steady state a sinusoidal signal oscillating at 2 radians per second, and this guy will produce in steady state a constant current, okay, here, and therefore the overall response or the overall current through the 1 ohm resistor will be a sinusoid with a DC offset, okay, and that's what we call the current in the steady state. Okay, again, we have two sources, and from the mathematical point of view, we have two sinusoidal sources, okay, at different frequencies, because DC signal or DC input can be considered as a sinusoidal input with frequency 0 radians per second, okay. Again, so what we're going to do is we're going to consider one source at a time, which we can, because the circuit is LTI, and then apply superposition. Okay, so let's begin by killing the DC source. Kill the 8 amp current source. Okay, so by doing that, we will be able to figure out the component of the current due to the sinusoidal input. Now, if we kill DC source, this is what we have. Okay, this is the circuit. This is a current source, therefore killing it means replacing it with an open circuit. And once that's replaced by open circuit, this is the topology that remains. Here we have 18 cosine 2t volts, okay, and the parameter values are given here. Now, since this is a circuit with a single input at frequency 2 radians per second, clearly we can apply phasor domain analysis techniques because we're asked for the steady state current to figure out the component of the current I due to this sinusoidal source, which we denote by I1. And then we can do the same thing for the DC source and figure out the component, DC component, let's call it I2, and in the end we can figure out I of t by simply adding I1 of t to I2 of t. Okay, so to figure out I1 of t, let's move on to the phasor domain at frequency 2 radians per second. Okay, so what we have is the following circuit. Okay, so 3 ohms is 3 ohms because the impedance of resistors, which equals resistance, is independent of the frequency. How about the impedance of this inductor? Okay, the frequency is 2 radians per second, and by j omega L we have j 2 ohms, okay, for the impedance. Here we have 1 ohm. Here we have again 1 ohm. For this guy we have j omega L, which produces j ohms. And as for 1/4 farad capacitor, the impedance is 1/j omega C, which produces minus j2 ohms. Okay, and what we're interested in is this current, the phasor of I1. Okay, as for the source, we have 18 volts with 0 phase. Okay, now what's I1? It can be easily computed as follows. Okay, so let's call this current IS, okay, the current extracted from the input. So we can figure out IS by simply dividing the source voltage by the equivalent or effective impedance seen by the input. So IS therefore equals the voltage 18 divided by the impedance seen by the input. So that impedance equals this impedance 3 plus j2 plus this impedance here, and this impedance here is this guy and this guy connected in parallel. Okay, so what we're talking about is the following: 3 plus j2 in series with, okay, this impedance and that overall impedance connected in parallel. So we have one parallel with what? 1 plus j plus minus j2, so that makes 1 minus j. 1 parallel with 1 minus j. Okay, and this can be computed to equal 18 over, the denominator turns out to be 3.6 plus j 1.8, and that equals 4 minus j 2 amps. Okay, 18 over the impedance seen by the source. And once we have IS, we can compute I1 simply by current division. Okay, call this Z1, call that Z2. I1 equals IS times Z2 over Z1 plus Z2. Okay, hence I1 equals by current division 1 minus J, which is our Z2 in a sense, okay, divided by 1 plus 1 minus J times the current that we have just computed, IS. So that equals 3 minus J over 5 times 4 minus J2, and that turns out to equal 2 minus J2 amps. And in polar coordinates, that's 2 square root of 2, which is the magnitude, and the phase is minus 45 degrees. minus 45 degrees amps. Okay, so that's the phasor I1, from which we can easily obtain I1 of t, because we know the frequency, which is 2 radians per second. Okay, so let's write that down. I1 of t equals the sinusoidal with amplitude 2 times square root of 2 cosine. Frequency is 2 radians per second, so we have 2t, and we have minus pi over 4 phase. Okay, now let's move on to the DC component of this current due to this constant current source. Okay. Now let's kill the AC source. Okay, now this source is killed, and this is the only active source. In that case, what we have is the following circuit. That voltage source is replaced by a short circuit, and then we have 3 ohm. How about the inductor? Okay, now we know that now this is the DC source, and we're talking about steady state, therefore we're talking about the DC steady state, because the only source that's active in that circuit is the DC source. And we know that in DC steady state, inductors behave like short circuits. Okay. Okay, and this is our inductor. Or, as we said, from the mathematical point of view, this can be considered as a sinusoidal signal with frequency omega. With frequency 0 radians per second. Again, apply our impedance formula, which is j omega L. Omega is 0, therefore regardless of L, we have 0 ohm impedance, and 0 ohm impedance means simply short circuit. Okay, so everything fits nicely together. And then we have this resistance, and here we have the other resistor. Here we have our inductor, which is short circuit in DC steady state, and here we have a capacitor, which is open circuit in DC steady state. And this is the input that's driving the circuit at 8 amps. Okay, this is 3 ohms, this is 1 ohm, this is 1 ohm. And what we're interested in is this current flowing through this 1 ohm resistor. Okay, because of this open circuit, because of this capacitor here, we can simply ignore this branch here. And what happens is we have 8 amps, and that's divided between 3 ohms and 1 ohm. So clearly 2 amps will be flowing over 3 amp resistor, and the remaining 6 amps will be flowing over the 1 ohm resistor. And I2 of t can easily be computed to equal 6 amps. Okay, and then by superposition, okay, we can add I1 to I2. Okay, I1 is here, I2 is there, and the overall current I in steady state will be that sinusoidal with a DC offset. Finally, by superposition, we can now write down the final answer. I of t equals I1 of t, okay, the part of the current due to the sinusoidal signal, plus I2 of t, part of the current due to the DC input, and that equals 6 plus the oscillatory part, cosine 2t minus 45 degrees amps. Okay. So, by looking at the two examples that we studied in this hour, let's finish the lecture by the following conclusion. Okay, so this is the lesson of this lecture. In phasor domain, superposition is possible, more importantly meaningful, only for sources operating at the same frequency. Omega. If we have sources operating at different frequencies, the superposition is applicable only in time domain. Okay. For sources of different frequencies, superposition should be applied in time domain to time domain signals.